Hi, in this video I will show you something remarkable. Small pieces of matter and light behave differently from what we usually expect in everyday life. We built quantum dice to demonstrate how small pieces of matter and light behave. And in this video I will demonstrate how these dice work and what you can do with them actually. If you want to know more information on how to build the dice yourself, or how to use these dice to explain quantum cryptography or any other information, visit our website or visit us at the University of Twente. Let's start with a single die. When I turn on a die, it resembles something like a real die. You have 6 sides and the values of 1 and 6. And the opposite faces have their values summed up till 7. So nothing really special there. But the special thing happens when I push what we call the quantum button. Let's see what happens. If you now look at the die, what value would you see? Do you see something like a 6, a 1, or maybe even a 7? This is what we call a superposition. We resemble with this superposition every outcome of the die between 1 and 6. You could say it is all the outcomes at the same time. So this is already a bit different than you would classically see in a normal die. What happens if I roll the die? Let's see. If you now look at the top of the die, just like with a normal die, you will see a value of 4. But what happens at the sides, you will still see a superposition. What's the deal with that? Well, we did a measurement just yet by rolling the die and reading the top face of the die. What happens if I now roll in the same color again? Let's see. When I pick up the die, every face again shows a superposition. And if I place it again on red, I again see a state of 4. Let's check again in red. Again 4. So if I keep rolling in the same color, the outcome will also be the same. But what happens if I roll in a different color? Let's see. Hey, now I get a value of 6. So what happens is when you roll in a different color, there's a probability of 1 to 6 to get every value just like a normal die. Maybe you question now, what happens if I now roll again back to red? What would you think? Would it be 4 again? Hey, I now got the value of 3. So we learned from this die that if you measure in the same color over and over again, it will give you the same value, except when you roll the die in between in a different color. Well, this color, we call that a measurement basis. It's the case in which you perform a measurement actually. So this die represents somewhat like a real quantum particle, like a photon or an electron with a magnetic field. And there it does matter in which basis, in which way you perform the measurement. To demonstrate that a bit more clearly, we presented a couple of more measurements and we presented in the table, and you will see in the table that every time when you rolled in the same color, the outcome will be the same, except when you perform the measurement in a different color. However, I called these dice quantum dice, so they're actually multiple. What happens if I introduce another dice next to the first one? So again, also push on the quantum button with this die, and then I bring them close together, and you saw it already happening. I see again this superposition state. This value of 1 and 2 and 3 and 4 at the same time, but something else changed as well. We saw that the color changed, so that means that these dice are in a superposition together. This is what we call entanglement, a special superposition state between multiple quanta. But what's the effect of this? What's the result? Well, let's see. If I roll this one, for example, in red, and I roll this one in red, I see 2 things happening. Again, I read the top of the die to see the measurement. I measure 5 here and 2 there, in the red basis, in the red color. But I saw something else happening. The yellow color disappeared. So that means that these dies are not together in a superposition anymore. They're not entangled. We call this a collapse of the quantum state. However, what is the result of the fact that they're entangled? What's the impact of entanglement on these measurements? To do that, we have to do multiple measurements. So what we do is we re-entangle them again. The color again will be yellow, so this is the sign that they're entangled again together in a superposition. And when I roll them again, for example in yellow, I measure here 4, and here's the outcome 3. Still, you need a bit more measurements to decide what's really happening. So what we did for you is we did some multiple measurements and we present them on the screen. If you look at the measurements of one single die, they're still random. If you look at the color and the outcomes, you can't determine any pattern. And if you would look at the measurement for the second die, you won't also be able to detect any pattern. However, when you combine both measurements and combine them and you look closely, maybe you can figure out what's happening. I give you a hint. If you just look at the measurements when we rolled the dice in the same color, we will see that again, the outcomes of both dice sum up to 7. It resembles basically the opposite side of one dice. You could maybe describe it as this. When the dice are entangled, they behave, when you roll them in the same color, as if they're one die. So the way how you measure one die influences the measurement probabilities of the other one. And this resembles the behavior of small pieces of light and matter on the small scale. For example, if you want to measure polarization for photons or a magnetic field of spin particles like electrons. If you want to know more about how we build these dice, how you can build these dice yourself, or how you can use these dice to explain something about quantum encryption, you can visit our website or visit us at the University of Twente. Thank you.